Okay, so the new bit I wanted to talk about before you all fall asleep is about how do we use this to predict stability. Now, I think we talked before about how do you get this thing to go to reach an infinite value. How do we get a closed loop transfer function to reach an infinite value? And that's by making g times h equal to -1. Yep. When g times h is -1, that denominator becomes 0, so we have a problem. We've got a transfer function where output over input equals infinity. We've talked about that before a little bit, I think. So what we're looking at here is g times h. I've got a real interest in understanding what happens to g times h. And does it go anywhere near -1? Okay. So what I need to understand is how does -1 show up in the Bode plot? The Bode plots separate out amplitude from phase. So 1 clearly is 0 decibels, just thinking of the amplitude. The minus sign shows up on the phase plot as being minus 180 degrees. If you take a sinusoid and add 180 degrees to it, it's the same as flipping it over negatively. Okay, so our -1 point is an amplitude ratio of 1, which is 0 decibels, with 180 degrees of phase shift. So here's a typical set of data, and what I've measured here is the open loop response of a system. I haven't closed the loop yet. And what I'm interested in is, does this data get anywhere near -1? So I want to introduce two terms. Okay, the gain margin and the phase margin. So let me go back to that picture a minute. -1 is identified as 0 decibels and 180 degrees of phase shift. Let's see if we can find it. There's 0 decibels. At that frequency, what's the phase shift? So we come straight down from there to the phase plot, see where it intercepts, and we'll get a value for the phase shift. Respects for that one, and it's less than -180. We'll find out in a minute. That's a good thing. Let's ask the question a different way. When the phase shift is -180, what's the amplitude? And in this case it's less than 1. So that also sounds like good news to me. We need to measure that. And the things that we use to measure it are called the gain margin and the phase margin. The gain margin asks, when you've got 180 degrees of phase shift, how much extra gain can I put in before I get to 0 decibels? Okay. How many more dB can we add until the amplitude ratio becomes 0 decibels when the phase shift is -180? Positive numbers are good. Phase margin is asking a similar question, but it just says how much additional phase lag, remember that lag is negative, can you add to make the system just unstable? So we identify 0 dB and see, can I put in any more phase lag to get me to -180? If the answer is positive, we've got stable systems. Okay, and looking at this, when the phase shift is -180, There's a close-up of the amplitude plot, and you can see I've got a positive gain margin in that example. When the amplitude is 0 dB, and here's a close-up of the phase plot, you can see I've got a positive phase margin. Okay. I can now confidently predict, if I was to close the loop around that system and turn it into a proper feedback system, it would be stable. Okay. We can actually say a little bit more. The phase margin here looks to me like it's about 40 degrees or so. That's not an enormous amount. And that would be stable, but probably quite oscillatory. It'd probably wobble about a bit. Okay, and again, the gain margin here is really quite small. It's, well, I can't see the scale clearly on this, but it's probably about 10 decibels, which is not an enormous margin. So this would be stable in the closed loop, but it'd be a bit wobbly, it'd be a bit oscillatory. Measuring the gain and phase margins from an open loop frequency response plot lets us predict what would happen if we close the loop. Okay, you get the idea? We're just looking for -1 really. We're measuring how close we are to -1. Positive margins indicate stability. Negative values would say, I wouldn't close the loop if I were you, because this thing's going to be unstable. Okay. It's a little bit difficult. You need to get your thoughts sorted out about what's a positive margin, because with a phase margin we're talking about, can I put in a positive quantity of a negative thing? Okay, so we're talking about, can I put in any more phase lag? We don't really do Nyquist diagrams, but you can identify the same features on a Nyquist diagram. Phase margin is measured quite easily as an angle, and the amplitude ratio is the value when the phase is -180 and the gain margin is 1 over that. Okay, we're not really doing Nyquist diagrams, so don't be too concerned about that. So that's the last bit of frequency response information. We can identify system stability in a closed loop if we've got open loop test data. Okay. Gain and phase margins give us a numeric indication of how close we are to having an unstable system. The smaller the margins, the more oscillatory the response. There's a number of examples. There's a number of practical exercises on this website. Okay, I'll come back to this first one because I need to explain to you what to do in that one. If you look in that one, I know there are no aerospace students in this room, but I couldn't help myself. That's a Cessna 172 apparently, and its cruise conditions are 110 knots of airspeed at 3,000 feet of altitude, and when it's there, it's governed by that equation, or some bits of its flight are governed by that. Okay. What on earth is that? Well, this is an equation that relates airspeed to the elevator deflection. Okay. So I'm sure you can imagine, if you turn the elevators, the plane is going to go, I'm not sure if downhill is the right expression for aircraft, but it's going to go downwards. Most things when they go downwards will speed up. Okay. So there's a relationship between the elevator position and the speed of that aircraft. If you turn the elevators so it goes nose up, it slows down. This is the equation governing that part of flight. Okay, delta U is the change in speed. That's the thing we're interested in. The big capital letter things, XU, ZU and ZDE, are just constants that come out of that particular aircraft. Okay, there could be different numbers for different aircraft. And delta E is the elevator deflection, and that's my input quantity. So what I was going to ask you guys to do is to develop a transfer function for that and tell me how that aircraft works. Okay. It's not as bad as it looks. I'm not going to ask you to do that because half of you are asleep, but you're here, which is great. Okay. Have a look at it later when you've had the chance to recover from the project thing, because if you look in here, all you've got in here is what order is that, I know it's a partial differentiation, what order of differential equation is that? Second order. If you get in there and rearrange that, what you find is that is a straightforward second order system. There's a second order relationship between what you do to the elevator deflection and the speed of the aircraft. Okay. So you put in a deflection of the elevator, let's say, so you're aiming the aircraft downhill, it then accelerates. Okay, if you do it the other way, you point it uphill, it slows down, then it stalls and you crash and die. But let's not get there just yet. These are real flight equations, and when you first see these, they look horrible. Yeah? All those terms in there, they look absolutely awful. But if you have a look at that expression, turn the partial derivatives into real derivatives, and just look at, some of this is just constants. A lot of it's just like U0 is a constant, G is a constant, much of it is a constant. See if you can work out a transfer function for that aircraft behaviour. Okay, which I haven't done for you. And see what you think. And then if you want to be really clever about it, using a standard 3-term controller configuration, build a controller to keep its on level flight at fixed speed. Okay, because this is the stuff you can do now. Okay. Nasty horrible equation is actually just a second order system. It's not a big deal. You know about controller configurations because you've some of you at least have had a go at a few in the tutorial sheets. So you can build a speed controller for that aircraft which uses the elevator position as the, if you like, the way that you have to control speed is just by adjusting the elevator. Okay. So you can have a go at that. Like I said, I was going to make you do it tonight, but I'll perhaps not do that. If you look in the PDF called Cessna example, what you'll see is a dreadfully scruffy set of handwritten notes, which is a solution to that thing. Okay, but I'm warning you now, it's not easy to read because it was taken from we did it live on the document projector last year. The other thing I'd like you to have a look at is actually a past exam paper question. We've now done time response, we have done the S-plane, and we've done frequency response. Okay. And this thing is really quite hard to put all on the same screen, I'm afraid. But what I've got here is a set of 4 different time responses, a set of 4 different pole zero maps, and a set of 4 different frequency response plots. Okay. There are only 4 systems. So what I'd like you guys to look at is which ones belong to which ones. This will be a bit small, but that's, in fact, I should do this properly, shouldn't I? And do that. Here are the time responses, here are the pole positions, and here are the frequency responses. Tell me which ones go together. And I don't mind where you start. You can start with a frequency response plot, you can start with a pole zero map, or you can start with a time response. But Which ones go together? Do you want to do one? And then you can scratch your heads over the other. Let's... I don't know which one. It's just too much choice. Which one to start with? Start with A. Start with time response A and see if you can identify which pole zero plot and which frequency response plot all belong to the same system. Okay, and if you did that as an exam question and got it right, you'd get some marks. If you want the full marks, you'd have to tell me why.
No, I knew that.
What can you tell me about the time response A? Any features about that you can tell me? Is it stable? Yeah, it's stable. It's a stable response. These are all step responses, but I should have made that clear. It's stable. Anything else you can tell me about it?
Underdamped.
It's underdamped, which implies it's second order, yeah? Because it's obviously not first order. So it's a second order underdamped system. Is there anything unusual about it?
40% overshoot.
Yeah, it's just a bit floppy, isn't it? It's just a bit oscillatory, that thing, that's all. So let's just take that piece of information and say, well, I've got 4 pole zero maps here. Which of those would match up with it? Let me ask you about pole 0, 1. Would that match up with it? If not, why not? No. It's got a pole on the right hand side. What does that mean? Unstable. It's not that one. What about this one, number 2? It's got a pair of poles which are complex. They're in the left hand side, so it's stable. That's good news. Would that fit? I've got 2 poles, so it's a second order system. That's a good start. They're complex. That means it's oscillatory. So that fits as well. What do you reckon? Okay, let's put it in reserve and look at number 3. Any particular features of number 3 that catch your eye? Which pole is dominant?
The first order, the single one.
The single one, because it's at the origin. What gives you a pole at the origin? An integrator. Okay, so the behaviour of that number 3 one will be dominated by an integrator sort of response. Does that match up with this? Input step. If you integrate a step, do you get a thing like that? Nah, I don't think it's that one. What about this one? What's dominating that one? There's a 0 right on the origin, isn't there? What gives us a 0 at the origin? A pole at the origin we just figured out is an integrator. What gives us a 0 at the origin? Differentiator. Okay, what does that look like? There's a differentiator differentiating things in it. What do you get if you differentiate a constant? Nothing. So you should end up back at nothing if there's a differentiator there once all the transients have died away. This one doesn't, does it? This ends up with a fixed value. So I think it's that one. I think it's number 2. It's just a common or garden oscillatory second order system. In which case, which Bode plot matches it? I'm going to go back to get these slightly larger. Which Bode plot do you think matches that oscillatory second order system? X. Y. Sorry. No. For what reason?
It matches better damping.
Okay. What's the phase doing there? If that was just a nice plain second order lag pair, what values would you expect the phase to take? Do you want to change your mind? So I've got an oscillatory second order system that's lightly damped. So let's go through these. This is starting off, it's got a slope to begin with, so that's rubbish, isn't it? That's no good to me. This one starts off with zero slope, but that sounds promising, but it's already got minus 180 degrees of phase shift, and that doesn't tie in. This one's got a positive slope. Don't like the sound of that. This one has got zero slope, and it starts off at zero phase shift, and it swaps over to minus 180 degrees. I think time response A, pole zero plot 2, and frequency response plot Z are from the same system. Okay? You've only got to do 3 of these, and then the 4th one comes for free. Okay? But this is a legitimate, I think this was 2 years ago, this is a legitimate examination question for you, not just to sort of, because you've got a chance of guessing them correctly, you know, oh, A, 2, Z, that'll be fine. But to get the marks for this kind of question, you also need to tell me why. You need to tell me what your process of deduction is. Just going to go back to the time. You don't have to start with the time ones, but you can start with the phase, you can start with whatever you want, just as long as you can match them up. Who's going to tell me what's different about B? It settles to 0. These are all step responses. Okay. So something is bringing that down to 0. Have a thought about what might do that. Okay. What's different about C? It's got a positive gradient. The size of the output is increasing with time. It's still a bit oscillatory, you can see the wobble on it, but its output, this is in response to a step input, the output is increasing as time goes on. That should give you a clue. What about D? What's different about D?
Unstable?
Yeah. The output is not only, because this one's increasing quite linearly really, isn't it? This one's, the more you go, the faster it's changing. This one's looking like it's lost the plot a little bit. And also the numbers are quite large if you look at the scales. And we know from our first look that one of these systems is unstable because you identified a pole on the right hand side. And one of these time responses is unstable, so I think you can link. Have a go at them. As I say, the original plan, because I'd forgotten about the hand-in for your interims, the original plan was for you guys to work through this in this session. Okay, now, I'm quite happy to do that. I'm equally happy to suggest that you go and have a kip somewhere and get over the strain. Entirely up to you. If you want to hang about and do them, I'll stay. That's brilliant. If you can't manage it, then I'll see you next week. Nobody's moved. That's great. Yeah. Right then, you're staying, so that's good news. Some of you are packing up. That's equal. Is anybody staying to do these? Won't take us long. Yeah, a few of you at least. Okay. If you're leaving, can you just sneak out quietly? Let's go back then to time response B. Okay. Now you've got to tell me what it's matched up with. Give you a couple of minutes to sort it out while these guys leave. Different.
Doesn't it come back to 0? So we need before.
It's come back to 0, so there's obviously not that one because we've done that one.
I mean 4.
4.
Yeah.
That one. What? So why? What is it about 4 that you think brings it back to 0?
To be fair, I'm working off like it has a similar pattern, like a similar second order pattern.
Yeah, it's got the second order pair, which is what's giving us the oscillation.
And it comes back to 0.
What does that represent? Got an answer from any? You guys working on it? Got any ideas yet? Which one does B go with? B is 4. Somebody say.
You have
Why?
dominant 0 on the real axis at the origin.
That's 0 at the origin. That's a differentiator, isn't it? And when we differentiate a constant, it comes back down to 0. Okay, which Bode plot? There are the Bode plots.
W.
Why? W. What have we got? We got mixed opinions at the minute. Which Bode plot then do you reckon matches up with what you've seen? Okay, we've got this oscillatory sort of response that comes back down to 0. And we reckon it's linked with 4 because there's a second order pair here that gives us the oscillatory bit, but it's dominated by this differentiator. And differentiating a constant gives me nothing. So that makes sense, in which case, oops, excuse me, blast. Didn't mean to show you that one. In which case, which of these matches up? Somebody said W, somebody else suggested Y. Let's say, whoever it was said W. Can you just tell me why? What makes you think that?
Got the spike for the under damping.
Right, it does have that. It has the sort of the resonant peak, doesn't it? So that's a good clue. It's also got the fast change of phase. So I think that all ties up nicely with a second order pair with not very much damping. Okay, somebody else said Y. I'll ask the same question. What drives that decision? I can't remember who said what at the minute. Somebody said the Y plots. Anybody care to own up to that and suggest the reason behind that?
Would it be because the face
can't-
does it like so?
I changed my mind. Something to do with 90 degrees out of phase, and that's what differentiator does.
Okay, was that what you were saying at the front?
Yeah.
It starts off with positive 90 degrees of phase shift, doesn't it? And the only thing in the book, in the recipe book, the only thing we've got that gives us 90 degrees of phase shift right from the start is a differentiator. Okay.
It's a suspense that was killing me. It made me change.
It's just competitive stuff, this. Okay, so I think that's right. So plot B, time response B, goes with pole 0 plot number 4 and Bode plot Y. What I should have done, I guess, is to label the point. If you look at the Bode plot, it's also got this vertebrate corner in it, which is a negative going corner. The slope is changing negatively, and that ties in with a second order pair of poles as well. There's a second order lag in there, isn't there? You can see that happening, and to indicate that it's quite wobbly, the phase shift actually happens quite quickly. So there's lots of information in there that helps us. So, C. Okay, increasing with time, a bit oscillatory. Which one of the pole 0 plots?
Process of elimination is 3
We've got 2 left.
because it's not the unstable one.
Okay.
So it can't be the one with
Right, so it's not number 1
yeah.
because that's unstable. And are you sure this isn't stable? Because it keeps getting bigger.
Doesn't still do it in a linear fashion.
It's controlled, isn't it? It's what you might call bounded. It's a linear manner.
It's a symmetry and the other one doesn't have any.
Yeah, I think the key point that's been made is it's quite clearly it's not, although it's increasing, it's not unstable. Whereas D is the obvious other choice. You can see that that is getting increasingly worse, isn't it? The further you go along, the worse it gets. So, where were we? So it's not 1, it's not 2, we've done that one, so it's 3. So what's causing this? These are all step responses, aren't they? So what's causing this upward slope here, do you reckon? It's that thing, isn't it? Okay, there's an integrator involved in this transfer function. And if you integrate a step's just a constant once you pass the initial bit. So if you integrate a constant, this is an unit step, so integrating 1 with respect to time, you get 1t. And if you draw 1t, what you get is a line going up there with a slope of 1. Okay, so that makes perfect sense to me, that this integrator term here is dominating this. We can still see the effect of these two poles. You can still see the oscillation they're producing, but the dominant effect is that integrator at the origin. Okay, there we go, keep doing that. So which boat plot?
Would it be W?
W, let's have a look. Why?
Because it's still under damp because it's oscillatory.
Yeah.
And it does have the phase shift, so it matches up with like the oscillatory ones.
Yeah, you okay with that, everybody? We're starting off with, we've already got a minus 90 degree phase shift right from the get-go. And the only thing that'll give us that is an integrator. We've also got, there's lots of clues on this one, we've also got a negative slope right from the beginning, and that's again is telling us about an integrator, in the same way that this had a positive slope because of the differentiator, and to indicate the oscillatory nature and the low damping, it's got this peak on it. Phase shift starts at minus 90, goes through a very rapid change to minus 270, so that's 180 degrees of change, which is a second order kind of change, and that is exactly right. Okay. And the other one's obvious because it's the ones that are left over. Okay. D is clearly unstable, which goes with, where is it, number 1, because this has an unstable pole. There's no oscillation because everything's on the real axis, and it's slightly harder to figure out on the phase plots, but if you look at these, one of them's got funny numbers on it. It starts off at nearly minus 180, which doesn't make sense compared to everything else. Okay, and that's the unstable one. The right hand pole does funny things, it turns things negative.
So is your maximum phase shift going to be 90 degrees on a stable system?
No. The phase information from a pole in the right hand side carries a minus sign with it. So what would have been a positive real pole if it was on the negative side, we start off with 0. But because that first order pole is on the right hand side, we're starting off effectively with a minus sign, so it's minus 180. So that's why it starts at minus 180. Okay. In a sense, the fourth one is almost a freebie, because if you can do the other 3, it's fairly obvious it's the bits left over. So that's a really nice exercise to let you understand that because they're 3 separate things really, aren't they? You've got the time responses, you've got the S-plane, and you've got the frequency responses, but they're all describing the same thing. So you should be able to link them together and see which one of these corresponds to the other one. Okay. It wasn't the most popular exam question, I've got to say, based on the comments I got afterwards.
I have a question.
Yeah,
So you said you would only give marks if people explain why they gave the answer.
not only, you get marks just for getting it right,
Okay.
but to get the full marks, I want you to tell me why.
But if you write because it's the last answer left, you get.
If-
it is the logical.
The truth of the situation, if you've answered the first three, hopefully correctly, with a logical explanation of why, and you answer the fourth one correctly, and you say, because it's all that's left over, to be honest with you, that's a perfectly legitimate reason, and you will get full marks for it.
Fair enough.
Okay? You might choose to put a bit more information if you wanted, but so far as I'm concerned, it's obvious that the only ones left is really quite acceptable, yeah. Okay, interesting little exercise, helps us understand the link between the three different ways of describing a system. Now, I think I'm actually going to suggest that we'll come back to the Cessna later. Okay, but do have a look at this equation, because if you're anything like me, the first time you see that equation, it looks awful, just because of the way it's written. Okay, but have a good look at it, see if you can make sense, and the document that's got the solution, although I wasn't really going to include this one, but I'll let you see it. Whether you can read it or not is a different question, I think. That leads you through finding the transfer function. Don't worry about the rest of it, because I haven't given you the required performance information, but it does tell you how to there's our three-term controller going on here, and it lets us decide exactly what values we put in for our controller to get this aircraft speed control to be done using just the elevator as an input. Okay, so again, this is trying to lead you through the whole process, really, of here's a horrible, nasty equation describing my system, how can I control it? Have a look through that. Sorry about the handwriting, it was kind of done on the hoof in here. I had every intention of typing it up prettily, but it didn't happen. So, but see if you can make sense of it. Right, thank you very much.